Hello, everyone, and thank you for attending today's webinar, The Future of Model Efficiency for Edge AI. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Armina Stepan. I am a staff marketing coordinator here at Qualcomm Technologies Netherlands, and I'll be the moderator today. Before we get started, I'd like to go over a few housekeeping items. At the bottom of your screen are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout this event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the widget and then click the submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical problems, please type your issue into the Q&A widget and we will be glad to help. I would like to now introduce our two presenters for today, Thymen Blankeford, Director of Engineering at Qualcomm AI Research, and Chirag Patel, Principal Engineer and Manager at Qualcomm AI Research. Thymen, please take it away.
Great, thanks a lot for the introduction, Armina, and welcome everybody to this webinar, where we'll be talking about the future of model efficiency for Edge AI. Very exciting. Let's see if the slides advance. Are they now advanced? I don't see it.
Yeah, so
Armina?
You're on slide number 2
okay.
right now.
I don't see the slides advanced, but I'll try to figure it out. Okay. So this is the agenda for today. We have two presenters. Myself, I'll be talking in the first part, and in the latter part of the presentation, Chirag will be talking about the AI Model Efficiency Toolkit and AIMET, and in the Model Efficiency Zoo. So I'll be talking a little bit about why model efficiency is important for on-device AI. I'll try to give an overview of integer quantization and floating point quantization. I'll show you some techniques that we've recently developed in improving low-bit quantization. And I have some comments, and Chirag will have some comments later about AI Model Efficiency Toolkit in a Model Zoo. And afterwards, we'll be addressing some of the questions that you can ask in the chat. All right. So I have a little bit of a technical issue here, Armina, because I can't see the slides advance. So I can press the button, but I can't see any slides change.
Yeah, refresh your browser, please, Thymen.
We see that artificial intelligence is, of course, being used all around us nowadays. So you can't find a smartphone anymore that doesn't have AI algorithms in it to enhance your photos, to analyze your text, or to help you type things. Smartphones are very common nowadays, with many applications having AI in those as well. Even as we're video conferencing now, as you see me, probably some AI process running in the background, enhancing images, compressing audio, and enhancing the overall experience. And what you also see is that AI is like changing a lot of businesses. So you can't find an automotive vehicle anymore without AI in it. So just like the big IT wave with having computers everywhere, every computer has AI now, and AI is everywhere. And of course, Qualcomm, as us, is making chips. We try to manufacture chips for many of these applications. There's one little problem, however, with this really big trend, and it's that deep neural networks are incredibly energy hungry. If you look over the years, the amount of parameters in neural networks has increased. I don't like to use this word, but literally exponentially. So if this trend keeps up, then in a couple of years, we'll actually have such a big number of parameters in the networks that it matches the amount of neurons in our own brains. Now, the problem with this is that this takes a lot of energy, and it's very expensive to run some of these models. And that's a bit of a shame, because if you look at our actual brains are more than 100,000 times more energy efficient. So there's a lot probably that we can do to make these neural networks more energy efficient. Now, this is very important for us as Qualcomm, because we want to still be able to run these really large neural networks on edge devices like mobile phones, like cars, like robots, or drones, or any machine that you can imagine. But with that comes a lot of challenges. So we still want to make sure that those devices are very small and that your battery runs for a very long time. So in order to achieve that, we want to look at how can you actually improve the efficiency of these networks when you run them on these important edge devices. And it's not even only edge devices. Even if you look at data centers nowadays and like the big machines that are being used there to train neural networks, what you actually see is that the big neural networks might take hundreds of thousands, perhaps even millions of dollars to train. So to reduce that cost and to also reduce the energy consumption of our device in general, I think it's very important to look at energy efficiency, even at the larger scale devices. So in Qualcomm, in the research department that I'm a part of, and also the other parts of the company, we take a very holistic approach to model efficiency. So we want to make these big networks as small and efficient as possible, and we do this over multiple different ways and different axes. So we have a lot of research and work being done in neural network compilation, in things like neural architecture search and conditional computing, all different ways that you can make your neural networks more efficient. And also the presentation topic for today, neural network quantization, which is what most of this presentation will be about. In my mind, neural network quantization is probably the most effective way to quantize your neural networks. So if you want to get the best bang for your buck, the best optimized network with the least amount of effort and energy spent on it possible, and neural network quantization is the way to go. So we see that over the years, we've actually done a lot of research in our research in Qualcomm on neural network quantization. Here's a short list of some of the papers that we've published in this area on the top conferences of artificial intelligence in the world. And in this presentation, I'll mostly be talking about the last two papers, Overcoming Oscillations and FP8 Quantization, published at ICML and NeurIPS this year. Now, what's pretty cool about all of this research is that we're putting a lot of this in the open source domain. So the base code for each of these papers is being open sourced separately. And then many of these tools actually make it into our professional neural network compression and optimization library, AIMET, that Chirag will be talking about. So we're very committed to making all of these new research methods and techniques that help you make your networks more efficient actually available to the general populace to help everybody out. It's very important for us that we do this. Now let's talk a little bit about neural network quantization, the chief topic for today. And the idea of neural network quantization is really easy. Mostly neural networks are trained and ran on 32-bit floating point devices. So every number in that network is represented in 32 bits. But that's a lot of bits. And you probably don't need that many bits to train your neural network or to run your neural network. So you can actually do 16-bit values instead. And that gives you a 4 times speed up in your network. It gives you a 4 times energy savings as well, or in some ways, 4 times increase in performance per watt, if you want to call it that. But you also can just think of it as your network gets 4 times more energy efficient, or just 4 times faster if you do 16 bits. The nice part of 16 bits is it's actually quite free. So you can just run your neural network, your 32-bit network, in 16 bits with almost any effort spent on it. It's very free to do so. Now, if you're willing to spend a little bit more time on quantization, not a lot, a little bit, you can actually run your networks in 8-bit integer format as well. And that's actually a 16 times speed up. So that's a really big factor, right, compared to the 32-bit floating point values that the networks are normally running. And now if you want to go really the extra mile and really hyper-optimize your network, you can even go down to 4 bits, which I'll talk about later in the presentation. And that gives you a 64 times speed up. It's very significant. So one of the only issues is that if you run these neural networks in lower bit widths, it might be that you lose a little bit of accuracy. And most of this field of quantization is about how do we get the original accuracy of your model back while still having a low number of bits. And that's what I'll be talking about in this presentation. All right, so before we head into the presentation, 2 important parts to understand, so you understand all of the techniques and methods that I'll be talking about. We generally simulate quantization. So, of course, on the device, things are actually run in a simulated format, like in a quantized format. But we try to simulate this on our training devices so it's easier to work with. Now, in the simulated quantization, or in quantization in general, you can actually quantize 2 different things. You can quantize the weights. Those are the parameters of the network. You can also quantize the activations. The activations are essentially the input image processed by the weights in every layer of the network. And these can actually be quantized independently. So you can have your weights in 8-bit, for example, and your activations in 16-bit, or your weights in 4-bit and your activations in 32-bit if you want. And I'll be showing some of these differences in the presentation as we go. So mixed precision is what it's called, having different bit widths and different activations and different weights and different bit widths. And you can also do this for every layer, and then it's called mixed precision. So one layer you might be doing 8 bits, and another layer you might be doing 6 bits, or 16 or 32. The other thing in the quantization world that's pretty interesting is that we have 2 types of tools, roughly. So if you want to quantize your neural network, you want to quantize it more than, let's say, 16 bits, you have to use a few tools to make this process a little bit more seamless and to keep the high accuracy of your network. So one class of tools is post-training quantization, and the other one is quantization-aware training. So in post-training quantization, we try to make the process as easy as possible, so there's not a lot of work on the side of the engineer. So you don't need the original training pipeline. Essentially, it's just like press a button, and then your network is quantized. So post-training quantization is the easy part. If you want to spend more engineering time on this, you can do quantization-aware training, and this is essentially training the neural network with quantization in mind. So there's a lot more hyperparameter tuning and longer training times involved. However, as a return, you get a lot higher accuracy, especially if you go down to, let's say, 4 bits. So with that in mind, I want to talk a little bit about floating point versus integer formats. And we've done research in this recently, and it's actually very interesting what comes out. So the common understanding is that floating point formats are in general better. So anybody I talk to about says, well, of course, floating point is more accurate. Why wouldn't it? We actually show in the study that this is not necessarily true, and the story is actually very nuanced. So going into floating points, what you see here is the integer format. So I hope I can actually draw this. I can't. Well, I'll just talk. So the integer format is essentially just a scaling factor, which is a floating point value, times a number of bits that you have, n, the mantissa bits. So for 8 bits, you can have 256 different values. The floating point format is very similar. It still has the same s and m, but it also has this number of exponent bits, so 2 to the power of e, or e to the power of e. Now, with the floating point format, you can change some of these mantissa bits to exponent bits. So what does this look like? Well, if you look at the format that you see here in 4 bits, you see for the integer format in the top, so S4, as it says here, the points are equidistantly spaced. Now, if you, instead of 2 integer bits, let's say have 2 exponent bits, you get a slightly different grid. Still the same number of points, but a different grid. So what you see is that the grid actually becomes larger than the original grid, and the points are differently distributed along this entire range. Now, one of the simple things you can do in hardware is you can change the scaling factor to anything, and it's super cheap. And so you can make this range the same range as your integer format. And now you see that the only difference between your integer format and your floating point format, so if you change the number of exponent bits, is where these points are distributed. So with the floating point formats, you're going to have more values close to 0 and less values further away from 0. That's really the only difference between the 2 formats. Now, what you see in practice is that you can change this format, and we'll be using this throughout the presentation, is to have a different number of exponent bits. So 5.2 means that we have 2 exponent bits, and 2.5 means that we'll have 5 exponent bits. And what's interesting is that most of the people that are promoting these floating point formats nowadays in some papers and in practice, they use these ladder formats with 4-bit exponents and 5-bit exponents. And we'll see that those are not necessarily better. Right, looking at some simple distributions. So if you have, let's say, a uniform distribution, you can see how good these formats are. So we can compare, let's say, INT8 to 2-bit exponents, or 3 exponents, or 4 or 5 exponent bits. And then we plot the SQ&R, or the MSE, the loss for these on the y-axis. And what you see in this bar graph, or this bar plot, is that for the uniform distribution, actually the integer format is the best. So if your weights or your activations are uniformly distributed, int is actually the best format. Now, in most neural networks, your weights and your activations are going to be Gaussian shaped, like in the middle format, like the middle distribution. And there, it's actually 2-bit exponents that are the best, with a close second to the integer format. And we see actually that the 5-bit exponents, for example, is actually pretty bad for this distribution. It's only when you add outliers into your distribution. So if you have a lot of values around 0 and then some outliers further away from the distribution, that's where your exponent bits are going to help. So the real takeaway is here that if your layers in your neural network, your weights or your activations have outliers, that's where it actually helps to have these exponent bits. The thing is, however, is that most networks are pretty well behaved. And many networks don't have these outliers in the layers. And even if they do have these outliers, they only occur in some layers. If you would run these networks that are very well behaved, that don't have these outliers, in your floating point formats with a high number of exponent bits, you expect them actually to perform worse than the integer format. So we can actually see this in the post-training quantization setting. Remember, this is the easy quantization setting. So we have a lot of networks here that we've quantized in PTQ. And we've plotted here the FP32 accuracy and what you get with the best FP8 format. And we see across the line that for the best FP8 format, the best result is actually quite close to the original FP32 accuracy. But what's interesting, however, is that what format is the best actually changes quite significantly. So for networks like ResNet18 and MobileNet-V2, we know that these are very well behaved. So these are very well behaved networks without too much outliers. So there, of course, the format with 2 exponent bits and 5 implicit bits performs the best. For BERT, which is a transformer language model, this is a lot of outliers. So here we actually see that having more exponent bits actually matters. Conversely, if you look at the other FP8 formats that are the worst, you can actually see that in some cases, the format that's the best for some networks is actually the worst for others, and quite significantly so. So for example, this 2.5 format for ResNet18 and MobileNet-V2 had a very significant accuracy degradation. So what we learned from this is that depending on the network and depending on the outliers in the network, one format might be better than the other. And there's no universal floating point format that's the best everywhere. So remember that some of these, that many of the discussions nowadays are about formats with 4-bit exponents or 5-bit exponents from some of the vendors out there. But those don't perform significantly better than some of these other formats that we have listed here. Continuing this, you can also do quantization-aware training. So this is where you train with quantization in the loop. And here, actually an interesting pattern emerges. So for both INT8 and floating point 8, we can actually get back to the original accuracy for these networks. And in most cases, except for BERT in this example, we actually see that the integer format is better than the FP8 format. Now you might wonder why that is. Well, if you're doing quantization-aware training, those outliers, right, that's the thing that makes FP8 better. Those outliers can be removed in the training process. So what we see across the board, and we have some more results in the paper, is that you, because of the quantization-aware training procedure, you actually remove the outliers. And across the board, we see that the integer format performs better than FP8 when doing so. Another thing you can do, so instead of doing the training, is that you can just run your net layers in a higher bit width. So for example, what happens if instead of like doing this INT8 format with 8-bit weights and 8-bit activations, you do 16-bit activations instead? Now what we see there is that for all of the networks that we've listed here, your 16-bit activation format gets your original accuracy back with FP32. So for all of these networks, we get incredibly close, sometimes even like a tiny little bit better than your original network with your 16-bit activations. Now comparing that to the best FP8 result, you actually see that the 16-bit activation result is more accurate than the FP8 result. And on hardware, there's actually not a big difference between the two, between doing the 16-bit activations and doing FP8. So these formats are quite alike when it comes to performance, but your 16-bit activations are going to be more accurate. And the other nice part of the 16-bit activations is that you only don't have to do it for some layers. So I talked about this mixed precision before. Only for the layers that have outliers, you can increase the bit width to 16 bits and be OK. And this way, you can actually make your network still quantize very well in integer format, not needing your floating point format. Very similarly, you can actually look at what happens in 16 bits. So there's an IEEE standard FP16 format. And this FP16 format is fixed. It doesn't have the scale parameter. And what you see here is that the floating point format, because it doesn't have the scale format, there are many values that actually will never be used by a neural network. So there's many large values that can be represented, and also very small values that the neural network doesn't care about in terms of noise. So if you look at this, and for well-behaved distributions, so when you have just a standard Gaussian distribution, you expect actually only roughly 1/16 of your values in the floating point format to be used by the neural network. So what you see here in this plot is that if you have 1,000 samples from a normal distribution and you quantize those with an integer format versus an FP16 format, and we add one of these outliers that I mentioned, and you just move that outlier away further and further and further, that's what's happening on the x-axis. You see that if the outlier is not there, so it's 0, your integer format in blue is actually significantly better than your floating point format. So here in this range, you can actually see that float 16s, FP16 is comparable to INT12 or INT13, so having 12 or 13 bits. So you actually lose 3 to 4 bits when doing FP16 instead of doing INT16. Only if your outliers are very far away does floating point become better. And this happens at a roughly 500 in this graph, which is 500 sigma away from your original Gaussian. So these types of outliers never happen in practice. So what you see for normal neural network applications is that the INT16 format is actually just more accurate than FP16. There's no doubt about this. Only when you get extreme outliers that don't happen in practice does this change. Now, of course, for 16 bits, it really doesn't matter, because for 16 bits is a bit overkill, far more bits than necessary. But if you really want to scrutinize this, you see in these results, for example, that for mobile FP2, the INT16 result is exactly the same as our FP32 result, although with FP16 you get this tiny bit of degradation. It's not a super large difference, but it still exists. And it shows that actually INT16 is more accurate than FP16. The real gist, however, and the important takeaway is that INT16 is just more efficient on device than FP16. So it's more energy efficient and it's faster in terms of the multiplications if you implement this in idealized hardware. So in light of all of this, I would actually say that no, the floating point format is not better than the integer format for deep learning. And we would actually promote using integer formats instead across the board. Specifically, so if you look at the entire spectrum when doing quantization, we're always trading off power efficiency and latency and the accuracy of the model. And of course, the other important factor is the amount of work that you have to spend on getting these networks quantized and run efficiently. So this slide encompasses my philosophy a little bit. If you want high accuracy without any effort, then INT16 is the way to go. So it's more efficient and more accurate than FP16, and you can run anything in INT16 without any effort at all. Now, if you want to spend a little bit more time optimizing your model, and you can do that with, for example, the AIMET toolkit that Chirag will be talking about, INT8 is the way to go. You can quantize most of your networks in INT8. Perhaps in some layers you need 16 bits. That's okay. That's only a few layers. And INT8 is actually more efficient than FP8. And if you do QAT, it's more accurate as well. Now, finally, if you really want to hyper-optimize your networks, really drive down the efficiency, you can go down as low as INT4. You have to do a lot more work for this, and I'll show you this in the next few slides. You have to train this in mind. But if you're willing to spend the time on this, many networks run in INT4 as well. And you get, of course, like I mentioned earlier, 64 times speed up compared to the floating point 32 format. So these steps are really significant. I want to talk a little bit about the integer 4 format. So this is highlighting some of the research that we did in overcoming oscillations in quantization-aware training. And we're going to talk about how you train your networks to go down to as little as 4 bits. So one of the cool things that we saw training some of these networks in 4 bits is some really weird behavior. So you see the training accuracy on the left, and the training accuracy during training for these networks is super fine. And then if you look at the validation accuracy, like how do they perform in the validation data set, this turned out to be super erratic. So there are a lot of jumps in the accuracy, going up and going down. So we asked ourselves the question, what is actually happening here? This is really weird behavior. So we dived into this a little bit. We looked at the last 1,000 iterations of training in MobileNet. And although the network is completely converged here and the learning rate is incredibly small, we still saw these weights in the network jump up and down very erratically. That's really weird because the network should have been converged and already in a steady state. However, we saw these jumps happening, these oscillations in the weights. Now, zooming in on this a little bit, if you look at the latent weights, so the non-quantized weights, they're all very close to the decision threshold. And sometimes they're a little bit above it, and sometimes a little bit below it. If they're above it, they will be quantized up. If they're below it, they'll be quantized down. And they keep on jumping up and down. that's really weird behavior. Now, these oscillations are very important because it turns out that these actually have a pretty big impact on the quantization-aware training procedure. So the fact that these oscillations happen causes two problems. One is that it corrupts batch norm statistics, and the other one is that it disrupts the model convergence. So the batch norm statistics are running estimates during training of some of the estimates in the network. But because the weights are oscillating so heavily, these estimates are actually wrong. Now, there's a very simple procedure that you can do to fix this. It's called BN, or batch normalization re-estimation. What you do here is you add a couple of data points during a validation data set, and you re-estimate these parameters. Now, if you do that, you actually significantly improve your performance, as you see in this table. In 4 bits, you regain 2% accuracy, and in 3 bits, you even regain 4.5% accuracy with this procedure. So this is actually very important to take into account, and it's one of the important findings in our paper, that this actually happens in practice. And we are actually the first paper that describes this effect of this quantization-aware training issue. The other thing is also very interesting, is that because these oscillations happen, even at convergence of the model, it disrupts the model convergence, so it disrupts the training procedure. So you can actually take this network that's still oscillating at the end, and then either find a better rounding setting, as you see here in this table with SR, or you optimize for the best rounding setting, which you see here with out-around. You can actually get significantly improved performance compared to the baseline. So you see here is that actually the oscillations prevent the correct convergence of networks on training. Now, in the paper, we have two methods to fix this. One is dampening, and the other is freezing. Relatively simple methods, but they work very well. The dampening method actually regularizes your layers to be closer to the actual grid points that you can represent in the integer format. So it kind of dampens away the oscillations. And then what you see at the end of the network, when it's trained, you get these very nicely Gaussian-shaped weights that are just not oscillating anymore. So that's one way, just regularize out the oscillations. And the other way we introduce in the paper is freezing them. So we keep track of the oscillations during the training. And then if weights are oscillating a lot, we just freeze them and keep them fixed through the rest of the training. And it also helps remove some of these effects of these oscillations. So if you look at these results tables for MobileNet v3 and MobileNet v2, looking at the MobileNet v2 table first, we compare actually with the state of the art in neural network quantization-aware training called LSQ. This is what everybody's doing. And then for 4 bits, you actually see that the batch norm re-estimation, BR, helps a little bit. But if you do this dampening or this freezing on top of it, it helps even more. So we get a lot closer now to the original floating point accuracy. And the difference is even bigger for MobileNet v3, where the batch norm re-estimation, the BR, helps a little bit on top of LSQ. But we regain more than 2% extra accuracy if we do this dampening or this freezing procedure. So we actually see with these results that we get state-of-the-art with these methods on 4-bit training. So really getting a lot closer to having 4-bit weight and 4-bit activation networks becoming the de facto standard for neural network quantization. So that's it from my side from the research point. So I hope that was informative and interesting, and I'm looking forward to the questions after the session. And now I want to hand over the proverbial baton to Chirag, who will be talking a little bit about our toolkit, the AIMET and the AIMET models. Chirag, take it away.
Yeah, thank you, Diamond. Hello, everyone. I'm going to talk about our open source projects, AI Model Efficiency Toolkit, AIMET, and AIMET Model Zoo. The projects are necessarily created to scale up energy efficient AI. Think of like democratizing efficient AI, right? And these are the tools of choice for that. The cool research Diamond talked about coming out of Qualcomm AI Research, right, forms the foundation of these open source projects. So at its core, what is AIMET? AIMET is a library containing state-of-the-art quantization and compression algorithms. Qualcomm Innovation Center has open sourced AIMET. It's available on GitHub for anyone to use and contribute. Typically, the way it will work is users have their own PyTorch or TensorFlow trained models. They can use AIMET to optimize these models and then deploy these optimized models on a wide variety of targets, whether it's IoT devices, mobiles, automotive, cars, and so forth, right? So let's take a look at the feature set. So a lot of our emphasis, as you saw from the earlier presentation, is on quantization. Quantization is the way to go. And then for that, we have state-of-the-art algorithms enabling both integer 8 and integer 4 quantization. We have algorithms in AIMET covering post-training quantization, like which are more user-friendly, easy to use, as Timon mentioned. Like algorithms like adaptive rounding, which for state-of-the-art integer 4 performance are there. We support mixed precision, automatic mixed precision, and then to make post-training quantization easier, we have something called autoquant, more of a push-button solution for post-training quantization. And to complement this for challenging use cases, or if users are willing to go the extra mile and get more accuracy out, we have quantization-aware training as well. So these are the core quantization algorithms in AIMET. To complement this, we also have some compression algorithms like channel pruning, singular value decomposition based, and also visualization tools that enable you to analyze what happens during the optimization process. So clearly, quantization brings a lot of benefits, right? Like by quantizing, you can reduce the required memory. The memory bandwidth when you are doing inference reduces. That translates to energy efficiency. And AIMET gives you all these benefits by maintaining the accuracy as close as possible to the FP32. This is really the key, right? Like to get the benefits, we also want to retain the accuracy. And AIMET does that. And we'll show you some data points as we go along on the performance across different use cases. Now, if we focus on the figure on the left here, right? So like the AIMET's algorithms, like compression, quantization algorithms are encapsulated in a library. And the library interfaces with like PyTorch and TensorFlow through APIs. The input will be a PyTorch TensorFlow model. The output also is again the model in the native format. And the APIs themselves are designed to be quite user-friendly, and then you can integrate AIMET within the existing user pipeline, right? So to illustrate this point, I would like you to focus on the right-hand side figure here. So what we are comparing is like the typical training flow in PyTorch. We'll have PyTorch model training pipeline with training function, evaluation function. And now on the rightmost column, if you want, it's the QAT workflow, quantization-aware training workflow in AIMET. QAT is nothing but like fine-tuning, right? So, okay, we ensure that you can fine-tune the network using the existing user's training pipeline. The only thing that changes here is you input a PyTorch model into AIMET. It will create a quantization simulation model by inserting quantization nodes at the right places. And then again, this is a PyTorch model only. So then you can use the rest of the pipeline again. The training function, evaluation function, the data loaders, all those things don't change really, right? So the point being, AIMET is designed to seamlessly integrate into the existing pipelines. We also have Jupyter notebooks and examples, both for post-training quantization and QAT available on our GitHub. So this will help you get started pretty fast using these techniques. So now I'm going to jump into more of use cases proof points, like what kind of performance can we achieve using AIMET. So the slide here shows recently we had done a demo of first 4K super resolution running at 100 plus FPS on mobile, right? So this came out of our Qualcomm AI Research full stack innovation. How do you optimize the models suited for hardware? How do you quantize them? And here AIMET was used to quantize the models in 8-bit using quantization-aware training. And you can see on the figure, right, the rightmost, the super resolved figure still retains the high fidelity that you care for after quantization. So AIMET's algorithms can help you meet your quantization needs pretty effectively, even for these challenging use cases. We earlier Timon mentioned a lot of the SOTA innovations on the enabling 4-bit weight quantization. So now we are bringing all those things into AIMET. Here you can see across broad range of use cases, classification, segmentation, super resolution, post detection, and we'll continue to have more data points. The accuracy for W4A8, 4-bit weights and 8-bit activation models, right? It's pretty close or comparable, less than 1% drop in a lot of these cases compared to FP32. So this clearly shows that AIMET can enable demanding use cases like segmentation, super resolution to 4-bit, which will even get further energy efficiency benefits, latency benefits when you run these 4-bit models on devices going forward. This slide is more about transformer quantization. The transformers, a lot of you know, are everywhere. NLP tasks, vision tasks, and they are becoming more and more popular as the deep learning progresses. If you look at the literature, transformer quantization is considered to be challenging. And now I'm happy to say AIMET is supporting transformer quantization. Like if you see the first 3 boxes here, they show results for NLP tasks We have popular models like BERT, DistilBERT, and so forth. The whole models can be quantized to 8-bit using quantization-aware training, and the accuracy again is very close to FP32. The rightmost data point is for a post-training quantization to highlight that, oh, even post-training quantization can work. This is a VIT vision transformer model, quite popular model. The people often go to that as a starting point. Here, using integer 8 and W8A16 mixed precision, we get a pretty good accuracy here as well, right? So AIMET effectively can quantize transformers as well. And I would encourage you to try for your transformer using AIMET. So AIMET is a collection of our state-of-the-art algorithms, right? Like coming from Model Efficiency Research. To complement these tools, we also have the AIMET Model Zoo available on the open source. So AIMET Model Zoo is a collection of pre-trained quantized 8-bit models covering a wide set of use cases here, like image classification, object detection, super resolution, and so forth. So, and together with like the optimized models, what we provide is like example recipes. Together with the Jupyter notebooks that I pointed you, there are some other recipes available here as well to quantize the models from FP32 to integer 8. So people can either use these recipes or they can directly take the pre-trained models and put it in their end-to-end use case. Again, we care a lot about accuracy. So when you do quantization, we don't want to lose accuracy, right? And here we are showing through our AIMET Model Zoo a wide set of models, like where on both TensorFlow models and PyTorch models cover like models like EfficientNet Lite, MobileNet V2, pose estimation, RetinaNet, even ABP and super resolution like models, which achieve accuracy less than with very minimal drop compared to FP32. So this proof point should hopefully convince you that, okay, quantization does not incur accuracy loss when you use AIMET and the right set of techniques. Talking more about super resolution, recently we released super resolution model suite in AIMET Model Zoo. Super resolution is a very important use case. You find it in mobile photography, XR, gaming, autonomous driving, and then also often considered to be challenging. So we released this a bunch of models covering different levels of complexity and accuracy requirements. And you can see across the board, the performance is very comparable to FP32. So pointing you to some of the resources we have to get you started on AIMET. Clearly, we have the AIMET available on the GitHub. It has a collection of it has documentation, tutorials, example Jupyter notebooks that you can get started with. Model Zoo will get you the pre-trained quantized models. If you want to directly use some of these models for your backbones, for example, or you want to take it into your pipeline and fine-tune them further for your end use case, you can do all those there. We also have a quantization white paper available, right? So think of that as a more of a practical guide to starting quantization using AIMET. So these are the resources available to get you started on your quantization needs very fast. I also want to highlight quickly Qualcomm's AI stack. The AI stack is designed for developers in the AI ecosystem to optimize and deploy their models efficiently on the hardware. Again, the AIMET here is a core optimization tool to enable efficient edge inference through quantization and compression. And finally, I would like to conclude, and then we can go to Q&A, right? So throughout the webinar, you saw like our message is model efficiency is key to enable on-device AI. And if you want to really make it more and more prevalent, energy efficiency becomes critical, and then you want to ensure that you can run the models efficiently on the edge devices. Qualcomm is AI Research is leading the industry in enabling this efficient edge inference, fixed point inference. We have results on INT16, INT8, INT4. They're pretty state of the art. You can see you can get the performance you care for. At the same time, I think again I want to reiterate one key message here, right? Like integer inference provides accuracy similar to floating point. There is no reason to believe that FP16 is better than INT16 and so forth. Integer inference is the way to go for energy efficiency for edge inference. And then AIMET is a vehicle of choice to quantize your models and get these benefits for energy efficient inference. So with that, I'm going to conclude the talk. I'll pass it over to Armina for Q&A. And please provide your questions on the chat box and we'll be glad to answer them. Thank you.
Thank you, Tamin and Chirag. There's quite a few questions that have come in, so we'll try to make our way through them. The first question, I think this would be directed actually towards Tamin. Well, to both. Let's say Chirag could comment on this as well. What kind of, sorry, now the question is a bit, what kind of tools does Qualcomm provide to check which layers should be quantized with a higher bit depth? So example given using INT8 and only wanting to quantize layers with outliers in INT16.
Good question.
I think Chirag can comment on this from the AIMET perspective. Yeah.
Yeah, so that's the exact reason why we have AIMET, right? To address this kind of need that users may have. We have something called quant analyzer available in AIMET. I didn't talk about it, but that falls under the visualization and the debugger tools or analysis tools that I mentioned briefly. You can use quant analyzer to analyze which layers are sensitive or not, and then run them in higher precision. We are soon going to have automatic mixed precision feature, which is available in some forms on AIMET today as well. So that will automatically figure out for you, okay, how do you want to run the whole network? Partition some layers into integer 8, some layers in higher precision. So we do have two tools available to address the mixed precision need.
All right, good to know. Thank you. Do you feel that quantization improvement works better than other techniques like pruning or flattening techniques? This is probably for the research team. Or do they need to go hand in hand, all of these techniques?
So this is actually a very, very interesting question, especially on the pruning side. So of course, the first step that you always want to do when you're optimizing your network is just to make your network smaller, right? So you can do that with NAS. If you're really into neural architecture search, you can just do it by manually tweaking some layers, removing some layers, and making. So that's always the first step that you should be doing. The second step is quantization. Now, compared to pruning is actually very interesting. So what we see in our results internally is that if you, let's say, prune a network by 50%, or you quantize the network by 50%, you're actually almost always better off quantizing the network instead of pruning it. And that's for two reasons. One, you actually get a better accuracy trade-off of doing quantization than that you're doing pruning. So if you do, let's say, 75% pruning, you might as well just have quantized 4 times smaller, right? But also in hardware, when you're designing hardware for this specifically, quantization is a lot easier to use than pruning. So with pruning, you always need to have a pruning mask on the side, like to indicate which values are pruned away and which are not. And implementing hardware that uses these pruning masks very effectively is quite expensive. So the hardware is not so very efficient. Whereas quantization is free. So you both get your calculations that are faster, your memory transfers is faster, there's no overhead there. So in general, I would argue that quantization is just a better way to go for efficiency than pruning by itself. On both axes, both in terms of accuracy, but also in terms of like the hardware that has to support it.
Clear. We've got another question coming in, and that is also for Chirag. How would AIMET do optimization of these models based on specific hardware? Does AIMET support a given set of hardware already?
That's a good question. So we typically, a lot of the algorithms we have in AIMET are hardware agnostic, but we do have some underlying knobs which allow you to configure depending on specific hardware. For example, if you knew this kind of layer fusions are going to happen on your hardware, we allow ability to configure it, and then it will comply with the hardware the runtime rules. So we do have ability to address hardware specific optimizations as well.
Right. So short answer, hardware agnostic. It's the way to go. How resource intensive is it to do quantization-aware training for INT8 for large models like GPT?
So, of course, if you want to 8-bit quantize your networks, and you can do your PTQ methods, right? And then it's not resource intensive at all. And some of these networks, like these language transformers, you can do just one 1/8 of the layers you can do in 16 bits, and the other ones you can do in 8 bits, and then this network works completely fine in 8 bits. So you can just do GPT with that if you want. If you want to do the training, it's just as expensive as you would do the training. So you can fine-tune your network on your data set that you want to apply your GPT for, but then in this integer format. And then you can get your GPT to work in int8 completely fine. What's the cost of it? Well, exactly the cost as you need to do your training with it, roughly that amount.
Yeah. Just as an overall question about floating point versus integer quantization, you are sort of debunking the commonly held belief that floating point would offer much more precision. Were you surprised by your research results?
Was I surprised? Well, I personally saw this coming to a certain extent, because if you understand the formats and what they do, you can quickly realize that these outliers are pretty important. And what I am surprised by is that many people feel that floating point is significantly better than the integer format for some reason. So I was not entirely surprised myself. I'm more surprised by the fact that the whole world seems to be thinking that floating point is better. Yeah.
I would like to add to that. Yeah, it was not surprising, but we did our homework and we showed the proof points, right, to convince even ourselves, make sure that we have the right intuition. Our intuition was right, and then that the results show that.
Yeah. You spoke about mixed precision accuracy and said that mixed precision, yeah, it yields very good accuracy. In fact, what are your plans with this format moving forward? And is this supported by AIMET?
So yeah, this goes back to an earlier question as well. Mixed precision, just Simon mentioned, it can give you the right trade-off, like in terms of the accuracy and the runtime requirements, also the amount of effort the user is willing to put in, right? Mixed precision clearly can help you balance all these requirements, and often is a choice that we encourage users to go for. AIMET supports mixed precision, like you can run the networks or optimize the networks in AIMET in INT8, INT16, and get that mixed precision model as an output from AIMET itself. Yes.
The next question is about transformers, transformer quantization. How did you, this is also for Chirag, how did you achieve that level of accuracy?
So yeah, I will add my thoughts, and then Timon can jump in as well. So for the results we showed, like quantization, we generally think, and our results are showing, experiments are showing that we do need quantization-aware training for getting the best possible performance with transformers. Often you can even like use mixed precision at higher precision, like W8A16 for some sensitive layers, and then even post-training quantization may work. But largely through PTQ, like mixed precision, and then quantization-aware training, we are confident we can get good performance on transformers.
Timon, would you like to add to that, or are you good with the answer?
Yeah, so we have a paper out on this called Understanding and Overcoming the Challenges of Efficient Transformer Quantization. So I'm on the paper, and also some of my colleagues, Jelise and Marcus. And essentially what we do in the paper is analyze if transformers can be properly quantized. And out of the box, there's only, like I mentioned, like one layer that gives issues. So all of the whole network is like well behaved, all nice Gaussian distributions, like I mentioned. And there's like one layer that has like these big outliers. And the moment that you get to fix that layer, either by doing very high bit mixed precision or by doing quantization-aware training, like Chirag mentioned, you can solve these issues with transformer quantization. And then if you look at vision transformers, so for vision applications, they have a little bit less of this outlier behavior, but it still exists. So for those networks, it's essentially the similar strategy that you can follow to quantize these, and then you can get them to 8 bits. And what you see is that even some parts of these networks can be run in 4 bits. And we even have experiments in the paper that you can do the initial embedding table in 2 bits even, and then your network is still completely fine in terms of accuracy. So you can find those results in that paper that I mentioned. Yeah.
Okay. Can you repeat the title of the paper and where we can find it?
Yeah, it's understanding and overcoming the challenges of efficient transformer quantization. A very descriptive title, and you can find it on arXiv. It's just Google it.
Yeah. Right. Sounds good. A lot of questions came in actually about this in different ways, but you've mentioned the results that you've achieved for INT4 quantization. Is INT4 quantization currently supported by AIMET and included in the AIMET model too?
So INT4 quantization is supported in AIMET. Post-training quantization techniques like adaptive rounding. They have seen to the adaptive rounding can be used to get good performance in a lot of the models. Quantization-aware training also is supported, and then that helps you get to 4 bits. In terms of the models itself, no, we have not yet released integer 4 models, but that is coming out pretty soon. So keep on the lookout, and then if you're interested, you can drop in an email, and we'll inform you also when we release them. So yeah, but it's happening pretty soon.
All right, cool. We'll keep an eye out. The next question that is for Timon. You mentioned these new methods that your team came up with, which are called dampening and freezing, used to combat quantization oscillations. Well, actually, it's a question for both. Is there a plan to implement these further into the Model Efficiency Toolkit as well?
I think Chirag can comment on this from the AIMET side.
So we are going to have these optimizations. So as I mentioned earlier in the previous question, right? We have QAT, and then we will also optimize it further based on the latest and the greatest research from Timon and team to incorporate some of these methods to even bring more models to work in INT4. So yes, it is supported, or it's going to be supported pretty soon in AIMET.
Next question is also about INT4. What is the next step in terms of quantization? Could INT2 show good results as well?
INT2, oh boy. Perhaps in some cases, where like especially insensitive layers, but really the lower bit widths you get, the more tougher your optimization becomes. So there's also a lot of people doing like binary networks and such. So then you have like INT1, let's say. But it's pretty tough to train these networks and get into the performance that is still good. So who knows? But I think INT4 is already a pretty difficult frontier that we're tackling now and that we're working towards to make that work for literally everything. I don't know if it's going to get better than that and if we can actually do binary for everything sometime. Yeah.
Challenge accepted, I guess.
Yeah, I guess, yeah.
You mentioned previously that quantization-aware training requires quite some effort. Do you see this improving in the future with new research or technology being released?
Yeah, I think so. Although the quantization training procedure that you have in this LSQ method, let's say, I think that's already pretty solid. And that works for many applications to get the accuracy up really high. So I think that in the foreseeable future, we'll probably get some quantization or training techniques that are like a little bit better potentially. So perhaps you can do something better with the scalar range learning, or perhaps you can do better when it comes to QAT and mixed precision. So I can see some advancements there. But I think the algorithms that we have for quantization of training are already very solid. And work very well in many applications. So I think there's still a little bit left to understand in the quantization world. But on the other hand, it might already be like 80% solved with all of the techniques that we have. Yeah.
I think we have time for one more question, and trying to kind of run through them. Some of them have already been answered in one way or another. All right, maybe this would be kind of a nice final question for you both. There seems to be a lot of industry chatter around FP8 quantization. Where does the analysis of the other industry, let's say, members go wrong?
Yeah. This is a really good question. So what I see is that there's a lot of vendors and people making hardware that are looking into FP8 as the next big thing. I think it's partially because like you're always looking for the next big thing, right? And to the next big differentiating factor. And FP8 sounds appealing, right? Because everybody's training in FP16. But I think where a lot of these analyses go wrong is that, like, if you're doing training with your neural networks, like this FP8 format is great for your gradients. So for training, especially for the backward pass, you see that the distributions actually have these big outliers, and this dynamic range is important. So there, definitely, if you're going to train, you quantize your gradients, FP8 is great. But for inference, it's not. That's what I've shown in this presentation. And then what you see in the papers of people writing about the FP8 format versus the INT8 format is that they don't make these proper comparisons with INT8 and FP8, like side to side, same training pipelines. And if they show results, then, for example, they would be only the results for like the language transformers and not for some of the image-based networks where these formats don't work very well. So where is it going wrong? Well, I think improper comparisons across the front, perhaps a little bit of a drive to really promote a new format. Yeah.
Clear. All right. With that, I think we will conclude. Thank you very much to Taman and Chirag.
Yeah, well, one tiny thing, Armina. For some of these papers that I mentioned, we also have the code available on github.com/Qualcomm AI Research. So if you look for Qualcomm AI Research on GitHub, you actually, even if the methods are not in AIMET, they might already be out there to some extent, accompanying our papers on the GitHub. So that's pretty useful to know for people.
Yeah, good one. So look up the papers with code on Qualcomm AI Research GitHub repo. All right. Thank you, everyone. On behalf of Qualcomm and our presenters, thank you for joining us today. The webinar will be available on demand, and have a great rest of your day.
Thank you, everyone.